So for this video, we'll follow up on stochastic models, and we'll start off by defining what a true value is, a mean, true value mean, residue variance. Then we'll also end for this video specifically, we'll end at standard deviations. So let's say let this here be a board, and from this here edge to this edge, let that be 10 meters, and let this be the true value. True in the sense that with reference to how a meter is defined, from this here edge to this here edge, in a perfect world, it's measured. Let's say for for the religious people, let's say it's measured by God. We get that true value as 10 meters. If 10 people measure this with let's say tape measures, 10 people if 10 people measure this distance with tape measures, let's say so 6 out of 10 measure this distance as 10 point let's say 10.03 meters. So all the 6 people with each with their tape measure measures this true value, that's 10 meters, as 10.03 meters. So 6 people have this measurement. Then of the 10, 4, so 4 out of 10 measure it as 10.00 meters. So 10 is the true value. 4 people have measured it exactly the way it is, having to 2 decimal places. Their measurement is not having any error. But for these 6 people, their measurement is having some error. So why am I doing this? I'm trying to introduce you to these two to these two words, which are precision and accuracy. So these 6 people, the 6 people's measurement of these 10 meters, their measurements are precise but not so accurate. These 4 people, on the other hand, are relatively, by relatively I mean when you're comparing to these 6, they're relatively less precise but more accurate than these. So it's like, so accuracy is basically how close you are to the true value, and precision is how clustered together your observations are. So if 6 people each made one observation, so these 6 people who are more than 4 people made observations that were clustered together. Yes, the 4 also made observations that were clustered together, but 6 is greater than 4. So relatively, when you're comparing the 6 to the 4, the 6 are more precise, but they are less accurate because uh, the error is equivalent to the true value minus the observation, or vice versa. You know, like error is absolute value, so it being negative or positive, it will just be error, because you really can't have a negative distance. It's positive, so you get the absolute value of the difference of the two. So this is basically how you define error, but I'll follow up in a bit. So this was just an introduction for this video. So let me make a few changes. Some signs you need to sort of memorize or just know at this sign. I think its name is mu. So this is used to refer to the true value. Then besides this, we also have an L written like so. This is used to represent an observation. Then L bar is basically mean of the observations. Then RI, this is used to refer to the residue. So this it's basically R, but that I is for, let's say, if you have an observation Li, let's say I can be any numerical value. Let's say, let me represent this as L1. L1. So the residue at L1 will be R1, which if you're using place values, it will have Ri. Yeah, so the I is just like there for representing the place value. It's like X if you're relating this to math. So now how then do these parameters relate? So the true value, what's the true value? The true value is really never known. It's only known by, if you're religious, it's only known by God. I like to say that. So if you make 5 observations, if you make 5 observations of, let's say, something, so meaning the average will be L1 plus L2 plus L3 plus L4 plus L5 divided by 5. So this is the average. And what this simply means is, if we were to refer to that board example I gave initially, if it was just five observations made and the true value is 10 meters, so if one measures 10.1, 10.2, and so on and so forth up to 10.5, let's say maybe one measures 9.9, 9.8, 10.1, 10.2. So the average of those is assumed to be roughly equal to the true value, the true value. So as you proceed, you make an assumption to say mu, which is the true value, is equal to the mean. So you make this assumption, and as you follow, as you proceed, this is what you relate the rest of the observations to. So then residue is equivalent to the observation. So let's say the first observation. So let me just give this its place value, its value. So the residue in the first observation is equivalent to the first observation minus the mean, which which you're saying is equal to the true value. So this is the first residue, and the residues follow up like that. So the residue in the second observation is equivalent to the second observation minus the mean. Yeah, and summation summation of the summation of the residues, you can write that like so. This is equal to variance to n. Let's say li minus l bar over, you can say, the number of observations. This will very soon change to the degree of freedom, but for now, let me just put it like so. This is equivalent to, you can also write this as n of ri squared over n. These two are the same, because it's just like this here is equivalent to that. So summation of this or these are basically the same. The number of observations, this is equivalent to variance. So this is basically how variance is defined. Variance is summation of residues residues squared, sorry, I think I missed the squared here. Summation of residues squared over the number of observations. This is one way to look at it, but as we proceed, it to be summation of residues squared over the degree of freedom. So that I will define as we proceed. So this is variance. Then now the square root of variance. This is the standard deviation. Um, I'll try to sort of define this in a visualized way, just so you can understand what's really going on. Let me just clear up some space. Let me use this here color, increase it a bit. So it's a yes, I think this will do. So let's just say we've got this, and let me still make reference to the initial. So if this is 10 meters, this is the true value. Let this be the mean. Then let me just dot out the other observations. Let's say here you've got 10.1, you've got 10.2, you've got 9.9, you've got 9.8. So the so again you have like the standard deviation, then you also have the standard deviation of the mean. Meaning, to start off, if you've got like, let's say this is the mean. So with the standard deviation, you have a value that you add and subtract. So let's say standard deviation is, let's say, 0.3. So meaning to the observation, to the mean, sorry, to the mean, you add it and subtract it. So meaning you add 0.3, you add the standard deviation, so you get to 10.3. Then this side you also get to 9.7. So this is like standard deviation is basically meaning all the other deviations fall within this range, something in those lines. So it, if you add it and subtract it to the mean, if you add it and subtract it to the mean, all the other range of values should at least fall within that range. And at times you might have something that's protruding. Let's say you had one observation that was either outside the upper limit or outside the lower limit. That's also accounted for if you, let's say, also account for the standard deviation, or sorry, the standard deviation of the mean. So meaning, yes, you've got the mean, but it's not just one value, it's also a range of values. So it's not really 10 meters, it's my range to like 10.03, 10.03, let's say here somewhere. Let me just change the color. My range to like 10.03, so here somewhere, and on this here part it might also range to like mm, what value is here? Just hold on. So, so let's say 9.97 to like 9.97. So 10.03 and 9.97 there somewhere. So you might be starting off from here heading into this direction, and what that would do is to just extend this line slightly this side, and on the positive, not on the positive side, on the upper limit side, it will also make an extension slightly. So this is just for visualization purposes. I'll explain it better in the video that follows. But yeah, hopefully this is making sense. It's an interesting course otherwise.